Let's dive into it. So we're going to talk about our Elasticsearch architecture, which we have here in Meltwater. And we could start with us. So here's Emre.
Yep. Hello, I'm Emre. I've been working with Meltwater for 5 years now, nearly. And yeah, I've been an overall nerd, talking and writing about techie and computer science things since 2002.
And me then, I've been here for 9 years at Meltwater, and before that at FindWise, so we have some former colleagues here. So I've been with Search forever, and Lucene since 2008, and Elasticsearch 2012 when I first joined Meltwater. So this is the outline of our talk. So first, a little bit on our use case, what we sell in Meltwater, and then immediately dive deep into the technical details, and then some on wildcards and searches, and at the end something about load balancing when you have a really large cluster, which is also an interesting problem. And then we have plenty of time for Q&A, I think so. But we will save the questions until later. All right. So here you can see what I would say our flagship application in Meltwater. This is just one out of many though, but this is the one we sell the most. So as you can see, it's a search and analytics application. So you put in some search boxes where we have different types of searches. It's the simple search, and you get some graphs and counters, and we have lots of tabs, lots of sources as well, and filters. So when I say sources, these are the sources we have, lots of them. And in total, all of this adds up to about 6,000 new documents per second. The largest we have is the entire Twitter fire hose, every tweet, every retweet, everything. We have also Facebook. That's not the entire Facebook, but it's a large portion. And yeah, you can see here, it's maybe not so impressive numbers, but these are very large documents. Like this can be 10-page articles or more. So they are a little bit different beast than these, but large variety of sources. And what do we do with them then? Yeah, we first acquire them. And we do that by crawling. We also buy some data, we fetch it, there are APIs, there's all sorts of ways to get the data. And then after we have the data, we apply enrichments on them. So here we have some enrichments we do are basically world class, best of the world, and some are maybe average, but still in total it's a very impressive set of enrichments we have. This is different teams. This is different teams. Then we come to our team to the left here, which is the search engine. So here we come into play, our team, my members, and we have roughly 400 billion documents in that cluster right now. And 4 million queries are executed. And it's all based on Elasticsearch. So this is how our cluster looks today, or almost today. I took a screenshot of our monitoring system, and we are running Elasticsearch 7.17 on Amazon. We use 3 available zones, as you can see here, and we have even distribution of clients and data nodes across all zones. So I think this is a nice number, 7,200 virtual CPUs. So if it's about, maybe 1,000 laptops if you have 8 cores in those. And 4 petabytes of total disk, and we utilize 85%. So that's 3.5 petabytes that we actually utilize. As I said, 400 billion documents. Because we use nested documents, it's actually 2.3 trillion LSC documents. But because we use nested documents. 5,000 indices, and for those indices we have 63,000 shards, 21 if we count the primers. And we try to keep to the recommended 50 gigabyte per shard, so that's why it becomes so many shards. And here, as I said, 4 million end user searches, but because we have so many shards, and because people search for very long date ranges, because we have date partition data, you actually become 600 million shard requests usually per day, which means 25 queries per node per second. Okay, so here's a normal typical view of how long things take to execute. So usually it takes just a few seconds, but sometimes it takes 5 minutes to get the result. So yeah, why is this? Yeah, Emre will maybe dive deeper into that.
So thank you. Now this figure, median of 0.5 to 5 seconds, it's really nice. This figure of 30 to 300, not so nice. So what's happening? First, I would like to tell a little bit about how do we actually execute searches. Well, in Meltwater, we do have not one, but 2 domain-specific languages where our users write their searches in. One is a language called the Boolean language that we expose to our end users directly. And then we have the middle language, which we call the runes language. And that's mostly exposed only to our internal development teams. An Elasticsearch meetup near 10 Göteborg by query basically gets rewritten on the way to a runes query, which is, when you look at it on the outside, it kind of looks like an Elasticsearch query. It's pretty similar, but it's different. Then, as you can see, it kind of gets grown up. One thing that gets added, and something that is not actually visible in this example, is that it also includes information about, for example, the analytics that the caller of the query might want. Like here, you cannot see anything about analytics, but when it's transformed, you have an analytics with it, so it can grow even further. And when you go one step more, then it gets transformed into an actual Elasticsearch query, then sent to Elasticsearch, which you cannot see here because it's just too big to fit on a slide. I mean, we tried with the best fonts we had, no way. So that's kind of the general idea of execution. And you can see that we have interesting operators in our language, like near/10, which gets translated to our runes operators and then implemented in Elasticsearch. And of course, a typical Boolean query looks like this, not like this. So you can see that it goes with like hundreds of terms. And more importantly, the part I'm going to focus a bit more on is the parts that we tried to highlight here. We didn't even manage to highlight all of them. There's some surprises if you look for it. But the wildcards are a part of our Boolean query language. And you can see that, for example, we can have very complicated operations, like not just Booleans, like or, and, not, etc., but also near/5, price, star, things like that. So how do those Booleans work? Like when you execute them, as I said, they get transformed into this. This one, I think it is not exactly the one I just showed you, but it is a very representative example. That's something that we got from our logs that we extracted. And it has 7.7 million characters in it, 10,000 terms, 1,000 wildcards, and 20 different aggregations. So yeah, it's big. So those wildcards, like we said 10,000 wildcards. or 10,000 terms and 1,000 wildcards, sorry. Our language allows us to have different kinds of wildcards. First of all, I kind of assume all of you know when I say wildcard, right? It's like either star for match everything that comes after that, or question mark for just matching one character, the classic wildcards. And they can be placed in different places. Like a wildcard, of course, classically can be at the end of a term, but it can also be in the beginning. Or we can have double-ended wildcards, where we have wildcards at the beginning and the end, or completely mixed stuff with the wildcards in the middle and the beginning and the end. One interesting thing we have is a custom feature that we implemented in our own architecture, and that's wildcards within phrases. So that's not something supported directly by Elasticsearch, but we do kind of manual work around it, where we get the wildcards, when we get the phrases and then split them into tokens and apply wildcards that way, which makes our queries grow even further. So that's a Meltwater custom feature, but that's a very commonly used feature. The problem? Well, you can see at the graph, like the graph goes from 1 second to 60 seconds, but the number of dual-ended wildcards, this is just for an example for that, goes from just 1 to 40. So it grows faster in the time dimension, more than you can add, faster than you can add wildcards, basically. They are slow. But why are they slow is kind of something that we need to define by going a little bit down under into how Lucene works. So Lucene doesn't actually have a concept of wildcards. It just has like terms, and then it matches those terms to documents. Where you index a document like with an ID 1 and the body of wildcards won't win. They sometimes do, but we want to claim that they won't. Elasticsearch basically creates a Lucene index, which keeps the reverse lookup of, okay, these are the terms, wildcards, want, and win. And then maps them to, okay, these terms exist in this document 1. Great. And when you try to query for a document with a wildcard, the first step Elasticsearch does is go through the index of all these terms, and find all the terms that matches your wildcard, so that it can turn your wildcard query basically to a term query. That's called wildcard expansion. And those expansions can become incredibly big. Like, in this case, we have a dual-ended wildcard where someone is trying to match everything that is somehow related to 2020s. You know, not many important things happened in the last 2 years. So yeah, this expands to 200,000 terms. So imagine running a terms query against Lucene that has 100,000 booleans, 100,000 terms in its one single big boolean. Not the best idea. And we learned it this way, because just for extracting those terms, building that huge boolean query, Elasticsearch needs to allocate memory. And when you build that huge query and try to match it against the documents, that's what happens to your memory. And that's what happens to your cluster. So this was when we were trying to kind of figure out the weak points of Elasticsearch. And we ran one query that was fairly loaded with a lot of stuff, and we didn't tune it at all at that point. This was the result we got. We got huge heap spike, and then a cascading failure on the cluster. And at that point, we had the max clause count set to 10,000. So, which means that when we are expanding wildcards, we are allowed to, Elasticsearch is allowed to build a query that expands to 10,000 terms which is too many terms, people.
Per wildcard, 10,000 per wildcard.
Oh yeah.
If you have 500 wildcard, 500,000.
And as I said, like the query I just showed you a couple of slides ago, that had 1,000 wildcards. So we had to find the fix, and we did. So the fix we found was using an Elasticsearch feature called index prefixes, which allowed us to reduce that memory usage. How does it work? Well, you basically trade off memory for disk. That's roughly the description of it. What you do is, instead of indexing the term monkey just as monkey, where Elasticsearch will try to match the wildcard monkey star, you index each possible prefix of the term monkey as a separate term. So instead of indexing one term of monkey, you suddenly have 1, 2, 3, 4, 5, 6 terms. A significant increase in your storage. But then Elasticsearch is smart that when it's trying to query a field that has index prefixes enabled, it doesn't try to extract all the terms from there anymore. Now it knows that index prefixes are there. So I can just get the term monkey, the 5-letter one, instead of trying to match everything that starts with a monkey and star, and match it against all the documents, which becomes incredibly fast. I will show how it impacted our cluster specifically. In our case, we have lots and lots of fields in our documents. Our document model is, the documents we store are pretty complex, but we do have a bunch of key fields like the content, actual content of the document, and title, and a couple of other places that is queried with wildcards very heavily. So we enabled this feature on those fields with minimum characters of 2 and maximum characters of 10. And now suddenly our disk usage grew with like 80%. Nearly doubled. The interesting part was it was 30% for our social content, while 200% for news content, which was editorial and like long form content, which kind of gives you an idea of how language is used between different platforms, because apparently social platforms have a much smaller vocabulary that they operate on. That was just a side effect and an observation. So once we have this, now we have no problems with trading wildcards at all. Because we have index prefixes, we can just match a single term in the index and then get all the matching documents. Perfect. What about leading wildcards? Well, we index backwards. We reverse the string completely and then do the same operation again, because, you know, if you can have double your disk usage once, you can double it twice. Why not? So these were the two major cases where we had managed to address our problems. But double-ended wildcards and the middle wildcards, they were not affected by this. So in those cases, we actually tried to tie down the Elasticsearch circuit breakers more, so that we put very strict limits on how many wildcards can exist inside terms or double-ended terms, etc. And in this case, we managed to stay safe because they are less used compared to prefix or leading wildcards. And then wildcards within phrases is basically, as I said, it was a functionality that we implemented ourselves. So if your phrase contains trailing wildcards mostly, that's fine. If it contains middle wildcards, then it has the same problems and the same circuit breakers involved. But overall, we got a very nicely performing cluster, I would say. And now we tuned our cluster to have the max clause count to be 2,000. So no wildcard can expand to more than 2,000 terms.
The default is 1024, so we have double the default.
And we have 8 million character limit on our queries and 70,000 terms and 30,000 leading or trailing wildcards. We can leave it very high, like 30,000, because we use index prefixes. They perform really well anyway. But then 80, not 80,000, just 80 dual-ended or middle wildcards, because they still carry the same risk of explosion, but that's kind of what we protect ourselves from by setting the max class count and the number of dual-ended wildcards.
Quick question.
Yeah.
Can we ask now?
Yeah.
What are you guys scaling on right now? Because this uses a lot of storage.
Nice segue, thank you. For the recording, the question was, what are you scaling on now? And I'll get to that. So this is not how our disk usage actually changed. This was something else, but this is a very representative of that change. So we decided to keep the image. So we are using 80% more disk due to index prefixes, and then 100% more again, just because we also index backwards. So suddenly our disk usage significantly grew. That's why when Karl mentioned in our introduction, we have like now 85% disk utilization. And that's not a problem because we used to scale on heap. If you remember, like when we expand wildcards, we allocate memory. So if we leave it like that, then we need to be able to always have some spare memory because some query might always come in, which expands to many million wildcards or many million terms and documents. And then you should always keep that spare space that you can use for handling that kind of big queries. That's why we used to scale on heap in our older versions. And that's how it looked. Like it was very, very unpredictable, the heap behavior. And this is how our heap looks after enabling index prefixes. Basically, it's flat. Like our heap usage, regardless of the queries that we take, we don't really have that kind of heap spikes anymore. We have much more predictable heap, which allows us to actually increase our heap. Like we now have 64 gigabyte JVM heap, 128 gigabyte of heap RAM that we can allocate safely to the JVM and the operating system caches without worrying about like if we can get just in case we get a heavy query or anything like that. And here is how we get the disk usage cost. We actually used to utilize a lot less of the disk, like 50% at max, I think maybe 45%. Mainly because we weren't able to store so much data because then it would, when on the query time, it would hit lots of documents and terms and then suddenly lead to lots of heap usage. And in the old versions of the Elasticsearch, we also had other things about the segment caches, but I'm skipping over that. In the latest versions, we still had the problem of like, if we have too much data on a single node, a single query might cause a lot of heap usage. Now that we address the heap usage, we can increase our disk usage to utilize the disk that we didn't use before. So now we are scaling on disk, which is a lot cheaper. We actually managed to scale down our cluster significantly since then.
Yeah, you see the scale down here actually.
Oh yeah.
You see in October 9, it had 360 nodes. Now we are at 300 data nodes, 325 total nodes.
Yep.
What about CPU usage?
This is actually showing the CPU usage. So we didn't see any big correlation, a little bit maybe correlation with CPU usage.
So
But-
right or it's like
So the purple is CPU and the blue is the number of nodes.
the scale is on right.
Scale is on the right, yeah. So 40%, 10%. So you see there is this weekly pattern, and you also see that, okay, here we start to be a bit worried. Are we gonna hit the CPU? But then the next week, so this was probably because of something else, not because of the scale on, but because of other. Yep.
Question, do you like play with reggae? Try to tweak there for the movement? Because then you can control the expansion by the regular expression itself.
No, we don't have support for regs.
Reg-esp is a query you can do, so you can put regex. The only thing is going to compare pretty much most of the interests in the inverted index.
No, we haven't tried that.
And
Yeah.
in the 7, because you guys are in the old,
Yeah.
so you have this option.
Yeah.
It's
Okay.
something-
We are actively working on utilizing the new features of Elasticsearch.
We are novices
So you
on the
guys
new
can
cluster.
try to
Yep.
tweak
Yeah.
in that one.
So what can if you managing this cluster in the particular locations and I'm using Elasticsearch from the different locations, then it will be impact your response time at that moment because your cluster is located in the different area and then you are searching from the different area.
Yes.
So in that situation, for the fast searching, you managing the same replication of the cluster to the different that location, or is the only the one single location?
Only one.
Only one single location. So we don't use any way of distributing it.
So,
And
so your static that previously shown the 0.5 microsecond will be vary on the different locations.
Yeah, the thing is that we have 2 layers above application layers, and they are also located in one single location. So
Okay,
So,
the result should be the response time. What I'm searching, the result should be the response time. How quickly is give the result to me? And you located your data center in the Sweden. I'm searching with the same website in the from US. The response time definitely will be vary. So
yes, and
Yes,
especially
yes, it
in maybe China or India, or we are everywhere. So yes, the response time varies, but
overall, I would say the speed of light doesn't involve that much difference when it comes to our users' experience. At least from our perspective, we haven't measured anything about that. We have upper layers on our stack that do some kind of caching that is closer to the users, for example. So our larger analytics dashboards that are mostly used in Asia and US, for example, they build their own caches. We have some custom solutions for the Asia Pacific region. They do build their own localized caches of the search results and things.
caching will impact for the new data when the new index will come to the picture.
Yeah.
Again, the caching will be awesome.
Yes, yeah, there are trade-offs, but right now we are going with this kind of architecture because it kind of addresses the latency issues enough for us.
yeah, it's.
What is it?
I think that is
Maybe we
included.
should move on. We can take some more questions after maybe 5 or so more slides.
Yep. So yeah, now that we don't have the spiky heap usage, we can scale basically on the very predictable disk usage because our inflow of data is roughly predictable. It doesn't have crazy spikes. So if we need to scale, we can plan it much nicer. And yeah, with all the data, we now need to arrange that data in good shapes so that it performs well.
So this is changing subject a little bit. So this load balancing problem is something we actually solved also in the old cluster, but we use the same solution here and to great value again. But to go back a little bit, this is actually a bit older data. So 9 million searches is actually 1 week of data in here because I took it a few years ago, this figure. But as you can see, this is the distribution of the sort of hotness, how often you search certain time ranges. So yeah, 1 week, very hot, or today. And then it goes down. So after 3 months, somewhere here, there are 2 million searches per week for 3 months of range. But you also see this very, very long tail. Some customers do search for 5 years of data. And 5 years of data is basically our entire cluster. So you have to search for 21,000 charts or at least 10,000 charts easily. So that use case also has to be acceptably fast. It doesn't have to be amazingly fast, but it has to be somewhat fast. And also we have to store all this data. Like we have to store all of it. So even if it's not so hot, we have to have it. So this is what we measured a while ago, that the hot data, which is red here, it uses 17% of disk usage, but 86% of the CPU. So it's not 100%, but it's still a very significant. And then we have this middle tier, where why we have that is because some of the social data we only keep for 15 months, and then it's not valuable anymore to the business. Like, it's too expensive to have it forever. So here we have the majority of the disk, and then we have the long tail, which is very seldom. But when you execute there, you actually need to return within at least 5 minutes, but preferably within 1 minute, and it's 21% of this. Okay, so this is not sort of the perfect fit for tiered architecture, or we have been working with this for years. And what we have concluded is this is the best architecture for our use case, is to have every single node have data of all classes. So the red here is these, the yellow here is these. So an equal mix of hot and cold data over all nodes everywhere. Okay, so this is the perfect scenario. How do we make Elasticsearch actually implement this? That's the hard problem. How to tell Elasticsearch to do this? Because Elasticsearch just sees charts and says, okay, there's one chart here, one chart here, one chart here. They also know the size of the charts, but they are basically the same, all of them, 50 gigabytes. So this is what we have done. So first of all, we actually disabled the built-in shard balancing. Otherwise, Elasticsearch was kind of working against us, and we had to tell it, stop doing that, I want to tell you. And then instead, we started iterating on this simple algorithm. There's actually a blog post only describing this, which you can get the link from at the end. But the Elasticsearch are good. It can produce you with statistics on the time it uses to search, the time it uses to index, the time it uses to merge on every single chart. So that combination of those three metrics we call hotness. So it's not only that you search a lot in the recent data, of course you index it much more. Then, of course, we fetch also the current cluster state and the current shard allocation, say, okay, these things are here. And then all of this data is fed into a linear programming optimization problem. So that is basically reducing the whole thing into a large matrix of ones and zeros. I think we have 40,000 in as an input, and that's about the largest we could do with this open source solver. So yeah, we were sort of a limit of, we could have used more parameters, we have to limit to what the solver could solve. And that's an open source one. And it is a Python wrapper on top of some C++ implementation. But after you put in all this matrix and the solver does its thing, in the end it spits out a number of moves. The solver, of course, needs to be tuned with some, I don't know, black magic. I don't know. And sometimes it's hard to make it do what you want to do, but it doesn't have to be perfect either. It just has to be better than what it is now, because you keep running it over and over and over. You never stop. You just always improve, always improve. Yeah, we use the reroute API to actually do the moves of the chart. And here's the results. So it was actually very hard to show the results because it keeps running all the time. We don't just want to stop them just to create a nice graph. But we had one instance a few months ago where we do the large-scale resiliency test. We turned off an entire zone, and then we turned it on again. And this is how it looked afterwards. And Actually, this is not the worst case. This is just somewhat bad. It can be much worse than this if we didn't have Chardonnay. Probably. We don't know because we've never run a cluster without this. So, but at least normal case, you usually are around. So brighter color are more nodes means. So if it's just a dark color, it may be only one node or a few. So some are up to 40% CPU, but most are around 20-15. But here we see an uneven cluster, and you see one poor node here had 80% CPU sometimes. And it's enough with one node being a bottleneck for everything to slow down because you have so many shards and you usually hit so many shards from the search. So very quickly you saturate the whole zone. And then if you have one bottleneck, yeah, then all queries will be slowed down by that poor guy. So extremely important that we have a good, and this will save money also, because if we can utilize our CPU as much as possible everywhere, then we can have less nodes and don't CPU bottlenecks. Also, as I said, we have to keep running this over and over again. So this is a typical sort of week or daily pattern that at 00 UTC, we create new indices. Those indices immediately become hot because they need to index a lot of data and they also start searching on them. So then every day we got this spike in the variance of the hotness. And then Chardonnay, oh, no, now I have to solve this, and it works for a while, and then it solves it in a few hours. And usually it doesn't move the hot ones, it moves the other thing around it. Because we don't want to move the hot ones because they are hot. And if you move them, you even slow down indexing. So you move the things around it, basically move other things out to make room for the hot one. And a lot of other things can happen. For example, here probably something else happens, some node left or joined, or some other disturbance in the system. Yeah, and indices are created, deleted, shards change size also across the day. The shard gets larger and hotter. So that's why we have to keep running all the time. And this is also my final slide, actually. But it's some statistics. So remember, we had 61,000 shards. And roughly every day, we move about 5% of all the shards to sort of continuously adjust. So yeah. About 2, it depends. It depends on a lot of things, luck, or I don't know, whatever. Sometimes it's 2,000, sometimes it's 6,000. Sometimes we do some tweaks. DS is trying to make it move less right now to save money, but it's a trade-off because you don't want to move so much because it costs money to move. Because Amazon charges for the network costs. so you want to don't move too much because it costs, but you still want it to be stable in the CPUs. So you also see you move most of the things early in the day, and then you have a period where you don't move so much. And then something happens at 9. I don't actually know what. But yeah. Amazon charges for network traffic. So it charges you to run a server, but it also charges you to move terabytes of data between.
Isn't it only between different rebuild zones?
No.
Okay.
The thing is that if you have 2 replicas and 1 primary, and then you have a replica in that zone and want to move a replica from zone node A to B, it will actually copy it from the primary. And it will charge you for the network from the primary. So even if you move within the same zone, 2/3 of the time you're actually going to be charged for it. Mm-hmm. Thank you, Amazon. But I think that was it that we wanted to share for now. And just before questions, I'm just going to advertise Under the Hood, meltwater.com is our blog. This blog post we released on Friday. So we're gonna have 7 different blog posts. We try to do one every Friday until Christmas.
Merry Christmas.
So we think we're gonna stick to that. we have promised on the internet now, so we have to deliver.
Can't lie on the internet.
No, exactly. If you're looking into this shard placement thing, it's actually old blog posts, but it's still relevant. Now, questions.
Yes. So since you guys are scaling on disk and you guys are optimizing for heat, or I'm guessing like heat and CPU usage, how do you guys balance for disk usage with Chardonnay? And is that an issue at all? Do you ever run into the issue where I've noticed?
Okay, so the question was, how does Chardonnay take into account disk usage? So it's actually weighted function, so everything matters. Disk matters, index hotness matters, search hotness matters. Then we have some other built-in heuristics, like at certain times per day, you shouldn't move so much because you're doing snapshots, or there is a lot of actual tweaks that we put into. And to be honest, some of it is a little bit opaque. Like we put in these heuristics, we put in these large matrices, and let the solver do the job. And then we see in the metrics that it works. Yes.
Yeah, I remember that when search also rejects sometimes those, right?
Yeah, those are also, of course, you are not allowed to have too many difference in shard count, and you cannot move the same index into the same node. So all of those parameters are also actually added to the constraints.
Have you considered like the trade-off of adding even more? That's kind of a similar question, but like more shards of everything, like just increasing shards even more disk space to not need Chardonnay.
Yeah, we could brute force, of course. Like we could brute force with a lot more hardware, but this allows us to save money. So effectively we are saving money by using Chardonnay. We could do it without it, but then we would have to pay a lot more money, and maybe also kind of poorer, worst case experience anyway. Yes.
You mentioned briefly at this table around age and CPU usage of the data that it doesn't really fit in tiers.
Usually when you have this hail, I guess, and what usually Elastic recommends is that you have one kind of hardware to have this data on, another kind of hardware to have this data on, and that. And we actually tried it and kind of experiment, but it never worked. Like it was never cost optimal. Like it always costed more than if you did this.
You can have everything the same, the same hardware, and just use the concept of tiers just to move the data around.
Yes.
So penalize the long ones.
Yeah.
Like I feel like to say so many things for you. It's like I'm a search specialist. I love search. And there is this new thing called a sync search, which is asynchronous. So it's done for those long queries.
Yeah. And yes.
So that's one of the things. Like, so how many of those old queries you guys run? Like that justify to just analyze?
A few thousand per day, kind of. A few thousand per day, I would say. Or maybe 10,000 per day.
Which is like 10% of the search?
Maybe 0.1%
What?
or 1%. Yeah, 0.1 maybe. So it's a few. It's few. So yes, definitely we are actually. It's one of our projects. Like so, we as I said, we very recently upgraded to 0.7, and we haven't been able to utilize any features from 7 really yet. We're like inheriting all the good things from the old system, and now we're gonna see how much better can we do. So one much better we're doing is this. Yeah, we didn't dare to be so tight first, but now we can tighten. So that's one part. But there are definitely more probably we could use. Yes.
Have you consider any like self-made tiering, like I don't know, ingesting the last row to another cluster of different sorts?
Yes, but not maybe to a deep extent, because this has kind of worked so good also.
Okay.
Like because we found a solution that worked in the old cluster, and it keeps working now because we have proven that it works. So yeah, why change something that works basically? Yes.
So if I understand it correctly, you two work
We work in the same team. Yes.
So, but you have something new, future, like some good project, or do you like?
What's the future?
A big company. I don't know if you have a name, but
the future is that we're gonna keep growing. We're gonna get more data, more search. Company for selling or what?
No, like if you say you work now with Volvo, Ericsson, something big company you're gonna work.
So we are employed by Meltwater.
Okay, yeah.
Yeah. So we're gonna probably, or I don't understand the question.
What is in the roadmap?
Yeah.
In the roadmap.
You can do something big.
So first of all, we have 30,000 different customers. So Volvo and Ericsson are already customers of Meltwater. So basically, you name it, there are, I don't know, but there are very many customers, and we as developers don't know all the customers. Yeah. But what are fun things in the roadmap?
I think we have lots of improvements coming up with the basically what's introduced in Elasticsearch 7. We have a whole huge agenda of things to try and see if we can get a better performing cluster by utilizing those features. That's one of the items that we have in there. And basically when we have that, so our team in our stack is maintaining the very core part of our business, but then there's lots of teams in Meltwater which build products over there. So what we do is generally to make those products possible.
So yeah, it was basically a search platform team where you can build things on top of. Yes?
It seems that you have it's quite predictive, the data, the amount of data you have, the number of nodes. Have you considered non-cloud solution?
Yeah, we started out in a data center in Oslo, but it was a company decision to move everything to Amazon. So, and that's keeps being our policy, and yeah.
And we got lots of benefit out of it also. Like it has its costs, but in many scenarios we made things possible that were impossible when we were running at the data center.
It's basically doing this migration, for example. We just said to Amazon, okay, we need 400 machines. Can you give them for next week? And they said, actually, we managed to tell Amazon, oh, you needed that much hardware. So is it okay with 30 days? So we actually managed to surprise them with how much hardware.
You can add to the story that when we were moving, we had 1,200.
Yeah.
And we wanted 400 more.
Yeah. Yeah. Exactly. So yeah, doing that in a data center maybe is possible, but you have to plan for it, and it's sort of something.
And especially in the past, our workload hasn't always been that predictable, or our growth of our cluster hasn't been very predictable either.
No, at some point we actually grew. So when we added the Twitter firehose, we had to grow the cluster 10 times within like 6 months or so. Yes.
I may be conflating like search volume with business value, but what's a business case for that long tail? Like, what's the business case for persisting that information if it causes so many engineering challenges?
It's because a big selling point is that we have all data. Like that's one of the. So we have all Twitter, and you have. So news we actually have back to I think the 80s.
1980s.
Yeah.
And yeah, we do have a customer segment that actually uses that data. So we used to have only until 2005 or something in the past, and then we had it as a separate project to actually have that extended because we had the business case for it.
But also it's quite cheap to keep that data to show.
It's like
it's only disk space.
It's only disk space. Yeah.
So we run like a quite big Elasticsearch at Record Future.
Yeah.
The same size as this one, and it was the same. We had the same setup and the same thing. So we tried also to run like on different machine instance types and things like that, and it didn't work out, or it didn't matter. So I think, like you're doing here, you're using the CPU, using for the hotspots, and then you're using the disk for all.
So
it's a good mix in Elasticsearch package.
If you don't have the old stuff, then you don't need to go through like engineering cycles to figure out how to
No, but the only thing you will save is on disk space. That's the only thing you will save.
Yeah.
So it doesn't cost that much actually. So it's keep
No, you use the CPU and the disk caches on this, and the rest are just basically laying there, and sometimes you're accessing. Yeah.
Do you have? I'm not sure you have that, but I guess different parts of the dashboard are run maybe by different teams. Do you have them working around your core API? Like they learn how your stuff works? Are they trying to abuse it or?
Yes, they are as well.
But like I don't know, in a clever way or.
So basically, we do have this layer, our own runes language that we expose to other teams in the company, and yeah, they find ways to use it very cleverly that we couldn't imagine. But that's basically how we interact, and that's a well-documented language at this point. So they can basically refer to documentation, and then they can always talk to us if they get stuck with something.
So yeah, so you can get sort of friction here, but I think that is usually manageable. The problem is here, like, and here we have customers and 2,000 sales representatives producing these, and that is a harder problem to actually tell them to do nice queries and teach them to do it. Yeah. And but now the good thing is now with the new system, they're not dangerous. The bad queries, they're just slow. They're not dangerous anymore. In the old version, it was both slow and dangerous. So now it's the right sort of incentive. Like if you want your queries faster, do this. It's not only sort of on us to panic in the middle of the night because the cluster crashes.
So it's supporting the multi-languages.
Yes, we have. I think we have. Maybe it says here. I think we have like 800 or 180 languages or something like that. And they are all on the same tokenizer. Right? All languages. Like there's no language specific. That's another blog post how we solve that actually. There is gonna write that.
I'm working on it.
now.
Maybe, yeah. Or how's the time? Should we try to wrap up or we can continue? Okay, if there are more questions.
So on this rune language or the system that runs it, any learnings on whether you move them now closer to Elastic or maybe or put more logic, like make it more raw Elastic or move it more to an application side of things?
Now we can ask Torsten. We actually have some hidden layers here that we haven't. I don't know. It's Meltwater. We have a lot of engineering teams. Like we have 35 different teams. So it's actually a very good thing to own this because then we can change things here without impacting all the rest of the people. So it's actually a necessity, I would say, in our engineering organization.
So that's only supporting the word search, not a phrase search.
So the phrase search, everything is going through that, including the phrase.
So the phrases we do support in the runes language. It's just that in this example it doesn't exist.
Yeah.
But the runes language does have support for phrases or wildcards and phrases.
Did that answer your question?
Yeah, I'm thinking that if someone wants to do some particular address search like the phrase, some content I put into some phrase search and want to do something search result, including that phrase completely, not a word.
Yeah.
I write the some phrase.
And we do support that as well. We have an extremely precise, like you can be so precise in the query language that you can imagine the problem then if you are precise, sometimes it's also very verbose.
Yeah, because initially I'm saying that you indexing the word like the monkey, M-O-N-K-Y, that is, but the phrase was not indexed.
No, the phrase is not indexed. So the phrase searching is solved by, sort of an upper layer where we.
Yeah, this is one feature I know, but it's not the right time to ask. But there is the future perspective if you are going to the growing. Maybe the scenario some company will ask to you, phrase can be searched can be possible, because the company have their own websites, they own their like the public forum over there, and something they want to be searched like the phrase search and content search.
Yeah, so something we have is we have a lot of brands. And when you search a brand, brands can be very strange. They can have like stars or dots or things in them, and they want only to search that and not all the other things that could sort of be reversed to that. So, and that is a common problem we have, but we basically have solved it with clever tokenization for now and expressive query language.
Sometimes you see that Google identify some calling with the pages, same pages is having a content search.
Yeah.
By using the same content, if you're using the same content with the two different URL, Google identify, oh, boss, you are using the duplicate phrase from this URL. You need to be stopped, otherwise I will stop you. So that was the content search. Full content, it was searched by the Google.
Yeah.
Not a word search.
Okay. Thank you very much for your questions and for listening. Should I disconnect?
Yes.
Yes.
Thanks a lot.